So for objective 3, we want to find the exact value of composite functions involving the inverse trigonometric functions. So this meaning that now we're going to use inverse trigonometric functions along with other trigonometric functions, not inverse, but different ones. So for our example, we want to find the exact value of sine of tangent inverse of 1/2. So let's go ahead and let theta equal tangent inverse of 1/2. That is usually the first thing that you want to do whenever dealing with inverse trigonometric functions. So we're going to let theta equal to tangent inverse of 1/2. Then, as we know before, you take tangent of both sides. And we can end up getting now instead tangent of theta is equal to tangent of tangent inverse of 1/2, which then gives us 1/2. So we can get tangent of theta is equal to 1/2, where theta is in between negative pi over 2 and pi over 2. This is because tangent of theta is greater than 0. So tangent of theta is equal to 1/2. Tangent of theta is greater than 0. So theta is actually going to be between 0 and pi half. So theta is between 0 and pi half, which means that theta lies in quadrant 1. So since tangent of theta is equal to 1/2, we know that tangent is equal to sine over cosine. So the only times that tangent would end up being positive would be in quadrant 1 or quadrant 3, but our interval doesn't even allow us to go to quadrant 3, so this means that we have to be in quadrant 1, which also means that sine and cosine are also going to be positive. So that's just kind of how we got to that point. So knowing this and taking this, we can say that also since tangent of theta is equal to 1/2, where we know that tangent of theta is sine over cosine, sine corresponding to y, and cosine corresponding to 2, which means that by having tangent of theta equal 1/2, this means that we have y is equal to y divided by x, where now y is equal to 1 and x is equal to 2. So using this, using that y is equal to 1 and x is equal to 2, we can go ahead and we can find the radius of this circle. So we know that the equation of the circle is x squared plus y squared is equal to r squared. We know that x is 2, so we get 2 squared plus 1 squared is equal to r squared. 2 squared is 4 plus 1 squared is 1. So we're getting that r squared is equal to 5, which means that r is going to be equal to the square root of 5. That's going to be positive because we only can have a positive radius. So our radius is now equal to the square root of 5, since we had this original value here. Also, as a side note, we can identify that because y is 1 and x is 2, this means that our point P is equal to 2, 1. We can know that as well. So we're going to take all of the information that we have just learned here, and now we can go ahead. We have everything that we need to solve our expression here. So we had sine of tangent inverse of 1/2. We let theta be equal to tangent inverse of 1/2. So what really happens here is that we have sine of tangent inverse of 1/2. Since we replace this with theta, we can now say that this is sine of theta. The thing that we were missing from having sine of theta was that we didn't know the radius. So now we are able to find the radius, which we know that sine of theta is just going to be y divided by our radius r. We know that y is equal to 1. So our value is 1 over the square root of 5. Now we don't like having square roots in the denominator, so we're actually going to multiply this by square root 5 over 5. So we get rid of the square root, and this gives us the square root of 5 over 5. So this is actually the value of our original function. So we can say, so sine of tangent inverse of 1/2 is equal to the square root of 5 over 5. So by allowing tangent inverse of 1/2 equaling 2 theta, we were able to go ahead and just find the pieces that we needed in order to find sine of theta. And those pieces were going to be the radius and the value of y. If it were cosine, you would need x and the value of y. Tangent, you would need x and y. So that is kind of how we used what we did before to just find important pieces of our problem. So all right, on to objective 4. Objective 4 is writing a trigonometric expression as an algebraic expression. So example 3, we want to write sine of tangent inverse of u as an algebraic expression containing u. So now we're doing the same thing. We're just using this arbitrary value u instead of x or theta or an actual value. So let's go ahead. So we can start by doing what we normally do, which is we're going to let theta equal tangent inverse of u. So using this, we know that we can, once we allow this, then we can get that tangent of theta is now equal to u, where we state our domain and our range. So we get that tangent of theta is equal to u, where theta is between negative pi over 2 and positive pi over 2. And that now u is between negative infinity and infinity. Since we stated that theta was between negative pi over 2 and pi over 2, we're just going to first acknowledge the fact that our values of secant theta and sine of theta are both going to be greater than 0. So then we can also take that our sine, let's put this down, our sine of tangent inverse of u, which we replace tangent inverse of u with theta, very similar to our last example. Now we're saying that sine of theta, and we're going to just begin to rewrite this. So sine of theta, we can multiply by any well-picked value of 1. A well-picked value of 1 can just mean that we can multiply anything by any equivalent of 1. So we can take sine of theta, and we're just going to multiply it by cosine of theta over cosine of theta. If we want to write out our answer as an algebraic expression, this just means that we need to have our final answer in only terms of u. We want to get rid of all of our trigonometric functions. So we're going to write sine of theta times cosine of theta over cosine of theta. This is now going to end up giving us tangent of theta times cosine of theta. Then, continuing on here, we can rewrite cosine of theta to be tangent of theta times 1 over secant of theta. Which then we can just say simplifies to tangent of theta over secant of theta. And let's actually move this down so we have some more room here to kind of write this out. So now we have tangent of theta over secant of theta, which using our trigonometric identities, we can say that secant of theta is equal to the square root of 1 plus tangent of theta. So using this, since we now only have tangent of theta, and what we established earlier was that tangent of theta was equal to u, we can simplify this expression to, this is tangent squared. We can simplify this to u divided by the square root of 1 plus u squared. So what we did was we took this original function and we just kept manipulating and kept rewriting it until we finally got into a final term where we only had tangents of thetas, which we were then since we were allowed to let equal to u, which is what we wanted. Our algebraic expression could only contain u, which is how then we had to get this final answer. So let's just reiterate that one last time. Let's write that out. So since we had that tangent of theta was equal to u, we want our final answer to have only tangent of theta. So we can simplify to an expression in terms of only u. So there we have it. That is how we would go ahead and try to rewrite a trigonometric expression as an algebraic expression. Really just knowing the difference is going to be the key there, knowing that you're going from trigonometric expressions to an expression with maybe just 1 or 2 different variables. So that would be the key there in that exchange. So all right, that wraps up section 7.2. So I'll see you all again in section 7.3.